Hello. In this video, we're going to present the Cauchy-Euler linear ordinary differential equation. So let's begin with the form. The Cauchy-Euler linear equation has the form an x to the n times the nth derivative of y plus an minus 1 times x to the power n minus 1 times the n minus 1 derivative of y plus, and so on, plus a2x squared times the second derivative of y plus a1x times the first derivative of y plus a0y equals 0. Here, a0, a1, a2, all the way up to an are constants. But an, the leading coefficient an, is different than 0. What we want to do now is to devise a method of solution. So we begin by assuming a solution of the form y equals x to the power r, where x is different than 0. We're looking for non-trivial solutions, so we want x to be different than 0. R is some undetermined constant which we are going to try to find. So when we see a Cauchy-Euler equation, we're expecting a power function as a solution. So we begin by plugging in y, the first derivative of y, the second derivative of y, all the way up to the nth derivative of y into our equation. To obtain a polynomial equation on R. That polynomial equation is called the characteristic equation. Our aim is to solve for R. Okay, let's do an example. Example, solve the given Cauchy-Euler equation. X squared y double prime minus xy prime equals 0. Let's ensure that we in fact are given a Cauchy-Euler equation. So we have x squared times the second derivative minus x times the first derivative. I don't see a y, so we can think of it as being 0 times y. So it does have the form. We have a constant times x squared times the second derivative plus another constant times x times the first derivative plus a constant times the variable, the dependent variable, equals to 0. So we confirm that this is indeed a Cauchy-Euler equation. So now we know how to begin. We make the assumption that a solution is of the form y equals x to the r. Now we find the derivative of y by using the power rule in this case. So y prime is r x to the r minus 1. We also find the second derivative of y, which is going to be, again by the power rule, r minus 1 times r times x to the r minus 2. What we want to do is we want to plug in y double prime and y prime into our equation. So let's write y double prime times x squared, y double prime times x squared, which in this case is going to be x squared times our expression for y double prime, which is r minus 1, r, x to the r minus 2. Now, we're going to multiply y prime by negative x. So y prime times negative x is negative x times the expression for y prime, which in our in this case, is r times r x to the r minus 1. So we get negative x times r times x to the r minus 1. Now we are requiring that y be a solution of our equation. So the combination x squared y double prime minus xy prime has to be 0. So this combining this left column produces 0. On the right, when we multiply x squared times x to the r minus 2, we end up with x to the r. So this first row becomes r minus 1 r x to the r. R minus 1 times r x to the r. Then we are subtracting x r times x to the r minus 1. Observe that x multiplied by x to the r minus 1 produces x to the r. So we end up with negative r x to the r. Now, in this resulting equation, observe that we can factor out x to the r, so we end up with r minus 1 r minus r times x to the r. Inside the bracket, we can do some algebra. Multiply r minus 1 times r, that gives you r squared minus r, but since you're subtracting r, you end up with r squared minus 2r. Now, so we have now that 0 equals this product, r squared minus 2r times x to the r. But since we are assuming that x is different than 0, we conclude that the only factor that can be 0 is actually the factor r squared minus 2r. As you can see, this equation we can solve for r. This is what we call the characteristic equation. So we solve for r. So we can factor out r. We have r squared minus 2r. We can factor out the r. So we end up with r times r minus 2 equals 0. Two solutions are r equals 0, and a solution is r equals 0, another solution is r equals 2. So therefore, we obtain two solutions out of this assumption. One of our solutions is y equals x to the 0. The other solution is y equals x to the 2. Consequently, since this is a second order homogeneous linear ODE, we have obtained a fundamental set of solutions, namely x to the 0 and x squared. But x to the 0 is simply 1, so we get the fundamental set of solutions 1 x squared. Our general solution is then a linear combination of these two. So the general solution of our equation x squared y double prime minus xy prime equals 0 is y equals c1 plus c2x squared. Let's do another example. Solve x squared y double prime minus y. Let's begin by noticing that this is indeed a Cauchy-Euler equation. You have x squared y double prime. You have 0xy, xy prime. Y prime is absent, so you could say 0xy prime minus y equals 0. So it is a Cauchy-Euler equation. So we plug in y equals x to the r. We assume that y equals x to the r is a solution to our equation. Now, first thing we need to do is find the first derivative and second derivative of y. As before, the r, y prime equals r x to the r minus 1, and y double prime equals r minus 1 times r x to the r minus 2. What we need to do is we need to multiply y double prime by x squared and we need to multiply y by -1. So let's see that. We're multiplying y double prime by x squared. Now, so what is y double prime? Is r minus 1, r x to the r minus 2. But we're multiplying that by x squared. Observe that when you multiply by x squared, so you end up with x squared times x to the r minus 2. That's just the same as x to the r. So when I multiply y double prime by x squared, I end up with r minus 1, r x to the r. Now I'm subtracting y, so that's the same as subtracting x to the r. As before, as in our previous example, since y is assumed to be a solution, when I form the combination x squared y double prime minus y, I should get 0. So when I combine x squared y double prime minus y, I should get 0. So that's the left-hand side right there. So that's 0 right there. Okay, on the right, we got to do the algebra. Notice that we have r minus 1 times r x to the r minus x to the r. We can factor out the x to the r. That's a common factor. When we factor out the x minus r, what are we left with? We're left with r minus 1, r minus 1. If we distribute, we end up with r squared minus r minus 1. That's our characteristic equation. So we get r minus 1 times r minus 1 equals 0. That has to be 0 because x to the r cannot be 0. That's our characteristic equation, which is r squared minus 1, r squared minus r minus 1 equals 0. We can solve that equation by using the quadratic formula. It doesn't factor, so we use the quadratic formula. After doing the calculation, we end up with two solutions. R equals 1 plus or minus the square root of 5 over 2. So there we have two solutions to our equation. One of them, y1 equals x to the power 1 plus square root of 5 over 2. Another solution, y2 equals x to the 1 minus square root of 5 over 2. We also get from that our general solution. Y equals constant C1 x to the power 1 plus root of 5 all over 2 plus another constant C2 x to the 1 minus square root of 5 all over 2. Okay, that's all for now. Thank you for watching.